Hello everyone and welcome to this video on reasoning with uncertainty, specifically covering probability theory. Let's begin with the motivation behind probability theory and how we can use it to reason with our knowledge. So the common example for this is a patient presenting a symptom to their doctor, and the doctor wants to try and figure out what condition the patient has. Sometimes this type of relationship will be expressed using description knowledge bases or description logic, ontologies. However, having a symptom only suggests a condition. It does not guarantee it. If you have a sore stomach, that doesn't mean you you're at the risk of your bowels blowing up, which is a thing of of a bowel blockage, for example. Having pain in your arm doesn't mean you're having a heart attack. It might suggest you're having a heart attack, but it doesn't mean it. So we have to be able to apply reasoning. We have some knowledge. What then is the probability of this condition being true? We have this whole list of knowledge, all these symptoms. What then is the probability of these conditions being true? How does the knowledge we have affect the probability of various possible outcomes? That is the idea behind reasoning with uncertainty. So using reasoning uncertainty, we model the world as a probability space. This specifically in this video, a discrete probability space, because that keeps the maths simple. However, much of the theory still applies to continuous. It is just more complicated to talk about. So a discrete probability space is how we model what is called a random action, which is an action with a non-deterministic outcome. For example, flipping a coin. So a random action is a action with a non-deterministic outcome. We can represent these by splitting them down into two parts. First of all, we have what is usually written using an S, which is our sample space. The sample space is all possible outcomes. So here we are dealing with a scenario where we know our outcomes. So if you flip a coin, you have heads or tails, and there's a very small probability of it landing on the edge. However, usually when we're representing this, for example's sake, we just say heads or tails. We're not dealing with situations where you might do something and an outcome you didn't predict occurs. We presume, for simplicity's sake, that we know all possible outcomes. We also have our P, which is our probability distribution, which is a function that assigns some probability for all of our possible outcomes in S, in our sample space. Some rules, these are probabilities we're talking about, so it has to have the sum of all elements, their probabilities, equal to 1. And each individual probability must be within the range 0 to 1, because otherwise you would fail that everything must be summing to 1 part. And of course you cannot have negative probabilities. Let's now look at an example of some such probability spaces. Probability space, discrete probability spaces. Got there eventually. Say we're flipping a coin. Again, very classic example. Now, of course, our S and our P. I'm going to actually two P's because there's going to be P of, well, let's draw S first. Our sample space is going to be equal to a head and a tail. So this is the two possible outcomes. You flip a coin, you either land on heads or you land on tails. And of course, again, we have the slight chance of rolling or landing on the edge, but we're ignoring that. So we see here an example of what a sample space might look like. We have heads and tails. So our sample space contains all outcomes modeled in some way. This is a very common way of doing it. We just have a letter that represents each possible outcome. This is the easiest way usually. And then, of course, we have to assign our probabilities for each. So the probability of landing on head and the probability of landing on tail. Presuming a fair coin, where each of these is equal to 0.5. and that satisfies each one's between the range 0 and 1, and their sum is equal to 1. So that's all good. What about the probability of flipping a coin 2 times? Well, to flip a coin 2 times, we need to first model our sample space. This is going to be equal. What's it going to be equal to now? Because of course we can't have heads and tails because, well, if you flip a coin 2 times, you're either going to land on 2 heads, a heads and a tail and a heads, or 2 tails. So we need to represent each of these, and we can just do them as I just said them. You can have heads and heads and tails and heads, and also tails and tails. This is perfectly valid. If you so wanted to, you could combine these two and say you don't care about order. In this case, order matters. The I suppose syntax for this sample space is first you have your first flyer land, the first coin landing, and then the second coin landing. Order matters. But you don't have to. This is the way I chose to model it. If in your situation that didn't matter, then you could model another way and simply have the probability of landing 1 heads, 1 tails be slightly higher, or double, the probability of landing 2 heads and 2 tails. So that is our sample space, and our probability then for each of them is going to be 1 over 4, because it's a uniform distribution, we call it. For such uniform distributions, there is another way to write it. What you can say is that for all of your inputs x from your outcomes x from your sample space, you simply have that the probability of x is equal to 1 over 4. And this will do the same job as what's on the left. Those two are both equal to each other. Use that there, red. Both work. The right's just a bit neater and requires less work, especially for sample spaces with many different things. But of course, it only works for uniform distributions where every outcome has equal chance. If I was doing the other model, which had doesn't care about order and simply had heads, tail, tails, head, wouldn't work because we would have, of course, 1 over 4, 2 over 4, 1 over 4. Finally, let's move on to a slightly more complicated scenario of rolling n dice. We don't know how many dice, just n. N dice. How can we represent this in our model of our sample space? Well, the way we do it, we say is S is equal to 1, we're shorthand, so we don't have to write all the individual elements because it is just a contiguous 1 through 6 to 6. And then we have this exponent style superscript n, which simply states do whatever we have before n times. As we had just now, this can be rewritten as heads, comma, tails twice. So same thing happening here, saying 1 through 6 n times for our n rolls of the dice. And then for our for our distribution then, again, presuming a fair dice, this is simply going to be the same as before. For all x from S, the probability of x is equal to, well, what is the probability of x? Of course, we need a uniform distribution. We're going to have everything be the same, but how do we know how to get that value? Well, what we can do is 1 over 6 to the power n. Why does this work? Well, the number of elements in our sample space sample space S is 6 to the power of n. And of course, each one of those is going to be the reciprocal of the number of elements. So this can be shortened to really 1 over the cardinality of S. Number of elements in S, the reciprocal of that is the probability of each outcome, presuming a uniform distribution. This is how you can figure this out. And of course, why is it 6 to the n? Well, above, when we were doing 1 over 4, why is it 4? That is because we have 2 possible outcomes, H or T. Two possible H or T, as we see here, 1, 2, and we have each one done twice. So we call this K, and we call this N. What we get is a probability of X equal to 1 over k to the power n, and this applies down here too. We have 6 possible valid elements in our alphabet, you could say, 1 through 6, and they are repeated n times, so you continue to get 1 over k to the n, or 1 over 6 to the n. Fairly simple stuff, just equations and combinatorics. Again, for the as a more intuitive example, you may see for HH, HT, TH, TT, that's binary. Replace the H with zeros and the T's with ones, and you have binary. 0, 0, that's 0. 0, 1, that's 1. 1, 0, that's 2. 1, 1, that's 3. So you can also see it as binary. It has the same reason that binary numbers can be calculated using the same formula of 2 to the power n. Now let's move on to events. Now events let us handle with more than one outcome. So what about if we want to talk about the scenario of rolling a dice n times and the probability of landing at least 1 6, for example, or flipping a coin 10 times and having 3 of them be heads, exactly 3 of them be heads. That would be two cases of events. An event is simply a subset of your sample space. Now, if we move on to the discrete probability space for the random action of flipping 3 coins, or the same coin 3 times, doesn't really matter, then you have your sample space of ht to the power of 3, or superscript 3, uniform distribution for your probability, so 1 over 2 to the power of 3, and an event, we use capital E to denote these, or commonly if you have multiple changes, but for generic event it's E, which is landing at least 1 head. So we're looking at the probability of landing at least 1 head, or the event of landing at least 1 head. What then is E? What is its value? Of course, it is a subset of our S, so we know that E is a subset of E. E is a subset of S. What can we define it as? What are its elements? Well, if it's getting at least 1 head, it is all combinations of, for example, heads, 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 that has at least 1 head in it, and so forth, and we get for all of them. It's all things apart from T, T, T. This is the only one that doesn't contain a head in it. So it's all elements that don't have T, T, T. That then is the event E. And the probability of the event E, which is the probability of E, is simply going to be the sum through all x's which are elements of E of those probabilities. If you have the probability of E occurring, is simply the sum of all probabilities within E. I think that's fairly intuitive, because an event will occur if any of its elements occurs. Remember, for a random action, only one outcome can happen at a singular time. So of course you cannot roll 3 heads and also 2 heads and a tails. So the probability of that event happening is going to be the probability of each of them happening together, or summed together. Now, some important operations to know is, well, these are events, so you can do all of your regular operations. But the operation I did just then, or the situation I did just then, of landing at least 1 head. If this was a more complicated scenario, or if you had a non-uniform distribution, finding that could be pretty difficult. There's a lot of things. So if you had a very large sample space, and you're trying to find, only one thing which isn't the case, that could be quite difficult. Common scenario, say you were trying to find this, but for 10 flips. In that case, there's going to be a lot of different scenarios you have to look at, 2 to the 10. And again, if they were non-uniform, summing all those probabilities, figuring out which ones they are, maybe if you're not certain again, it's complicated. What you can use is the complement to shortcut this scenario. This is the set theory complement. The set theory complement simply negates a set. So if you have a set with contains elements A, it is the complement of that set is a set of all elements apart from A. So if we want the probability of that E, this is simply the same as saying 1, which is the sum of all probabilities, remember? Or in other words, the probability of S, minus the probability of not E, which is 1 minus the probability of not E. In the example above, this would be probably a much more computationally efficient way of doing it, because there was only one element in the set of not E, because it is simply, as I mentioned, triple T. And the probability of triple T is just 1 over 2 to the power of 3. You have that one calculation to do, and then a second to do 1 minus that, and then that's it. Rather than that entire sum over all operations, which if you have hundreds of them or thousands of them is a lot of operations to be doing, much more efficient just to do 1 minus the complement. So complement can be used just as it can in set theory, and applies also the rest. I'm only going to only one I'm going to mention is union, just because we have it's based upon your usual way of finding the cardinality of the union of two sets. So if you have some E1 with some E2, the cardinality of that is going to be E1 plus the cardinality of E2 plus minus the intersection of E1 and E2. This can be directly converted into probabilities like so. And that can be extended further into, for example, three events. I'm not going to go into that. If you want to, I have a video on it on set theory. Look at that. The only other thing I'll quickly mention is disjoint events, because of course this final section, the intersection of our two events, if they have no intersection, if they are disjoint, then in that scenario, you're not going to have anything in this value. It's going to be 0, so the probability of that is going to be equal, to 0, which is you're not going to subtract anything, which is to say, for disjoint events, then you only have, this probability is going to be the sum. So you have the sum of the probability of each individual one, because it's this one plus this one. So be aware, if you have disjoint events, the scenario, the equation is the exact same as this one, but that final thing, the subtraction, gets removed because it's 0. So all you have is the sum of everything involved, which is in this case, E1 plus E2. So be aware of that. Otherwise, not particularly important. Let us move on to conditional probability. If we have the scenario of looking at families with 2 children, and we are modeling the sex of those children, so whether they are male or female. Our sample space then is going to be equal to this. You have 2 boys, a boy and a girl and a boy, and 2 girls. Again, here we are caring about order. Our probability is simply going to be our uniform, so it's going to be 1 over 4 for all x. And we are trying to discuss a scenario of the event of having at least 1 boy. Of looking at 2 boys, given we know there is at least 1 boy. So what is the probability of having 2 boys if we already know they have at least 1? Small typo there. So let's convert this into our probability format. So we have the probability of 2 boys. However, that's not enough, because we're not trying to find the probability of 2 boys. We don't know that. It's 1 over 4. We want the probability of 2 boys given the additional information that we know they have at least 1 boy. So we can remove this one, because that doesn't fit the scenario. We're told, we've given the knowledge that there is at least 1 boy. So only those first 3 are valid entries. So we want some way of denoting that. How do we do so? We use a vertical bar and then write down what we know, which is going to be at least 1 boy. Now, this isn't a very mathematical way of writing things. So we need some way of denoting our given knowledge some other way. Now, I've already mentioned we don't need to care about our final two girls scenario, so let's redefine our sample space given our new knowledge to represent what we know. So we have some S prime now. In fact, I will use a different color for this. We have some S prime, which contains simply our other three. This then is the mathematical version of what we had above. So we have this is now equal. So the same thing as before is now equal to 2 boys given S prime. So this is what we're trying to find. The probability of 2 boys given, and this is how we read this vertical line, it means given. However, you see we're trying to find the probability of 2 boys given that thing. Well, we have a problem. That thing, S prime, is a sample space now. It's a reduced sample space given knowledge, but it's a sample space. And it doesn't follow the normal rules, because the sum of all the probabilities within it does not equal 1. It equals 3 over 4, because it's only got 3 of the original 4 elements. That's an issue. We need to find a way of dealing with that. And we do so by individually dividing the original probability of each of our elements. In this case, we're only going to do it for the one we're querying, which is our 2 boys, by our new probability of our reduced sample space. This is called the process of normalization. So what we do is find the probability of our 2 boys according to our regular sample space, because it's not given anything. And now we're going to divide it by the probability of our knowledge, or S prime. And this will give us what we already know, probability of 2 boys, that's 1 over 4. And the probability of 3 of the 4 is going to be 3 over 4. And that cancels down to 1 over 3. So there's a third chance of, if you know there is already 1 boy, having 2 boys, which makes sense. It's a 1 in 3 choice from a uniform distribution out of our S prime. So this equation, this process, will reconfigure our original probability so with respect to our new set of probabilities, also our new set of knowledge and its probability of occurring, which is S prime. Or in other words, S prime is the event of having at least 1 boy, and we are reconfiguring our probability of having 2 Bs, or 2 boys, according to that event's existence. We know that event occurs because we're told so, and we will have the probability of 2 boys with respect to the probability of that occurring. That's what we're doing here. However, we still have the issue that using this method, the probability of 2 girls is still 1 over 3, because you just plug the numbers in and you get 1 over 3, because the probability of 2 girls according to the original is 1 over 4, which is the same as this one, and the probability of this remains 3 over 4, so you get the same answer in the output. That's not right. How can we fix this? What we do is just have a bit of a change, and make our numerator be with respect to our new set of knowledge, our new event as well. We have to treat it like a singleton, which is a set of only one element, so we can have it interact with our event. So we treat it as an event. That's pretty much. So we can rewrite it as the probability of 2 boys and union with or S prime. I suppose I should use the proper set theory notation, shouldn't I? There. All over the probability of S prime. And now, if you were to try that with 2 girls, you'd have the set of girl, unioned with the set of something which doesn't contain girl, which is an empty set, which is the probability of an empty set is 0 because nothing's happening, and 0 divided by anything is 0. So this would solve the issue, and for everything else, it just gives you the same thing of 1 over 3. This fixes the issue. This gives us an equation for conditional probability, the probability of some event A happening, given that we know that some other event B happens. Or conditioned on the fact that some event B happens, is why it's called conditional probability. Now, we're going to explore another concept which is called conditioning. Now, in this scenario, we are given 2 events, A and B. We want to find the probability of A. and we know the probability of B as well as the probability of A given B. So how can we use these equations to find that? Basically, what is the inverse of the process we just did? Well, if we're looking at this, the quick explanation is that if you have the probability of A given B, this is equal, as we've just determined, to the probability of A and B, all divided by the probability of B. And then if you just multiply the probability of B, which we have, you'll get back to the probability of your numerator, which is A and B. So you would get the probability of A and B. And of course, we know in this case A happens. I'm not sure if I mentioned that. We know, B happens. So we know that B occurs. I suppose that's implicitly implied by this line. We know B occurs, which is why we have as an aside, is why we have our A and B here, not just A, because we can't find the probability of A. Best we can get is the probability of A given B. Sorry, the A and B. Because we know B happens, and that could potentially influence A if they are in any way dependent on each other. If B occurring modifies the probability of A occurring in any way, if they are dependent, then we can't find A anymore using this maths. If they're independent, it's fine, and I'll get into that in a moment. But if they're dependent, then we cannot find A anymore, we can only find A and B. Anyway, quick aside into that, back to where we were. So yeah, if we have this equation here, then by rearranging this to find the probability of A and B, all we have to do is multiply the equation we had by B, and that just gives you the probability of A given B multiplied by the probability of B. Again, both things we know. We've been told those values. So we can find this. All good. Yeah, it works. Why does it work? Well, basically unnormalizing. By multiplying by the thing we normalized, probability of B, we have unnormalized. And of course, by the way, we're assuming the probability of B is not 0, in which case everything dies because division by 0. And additional point, of course, the order of conditional probability matters. A given B does not equal probability of B given A. Cannot swap them around. But probability of union doesn't matter. You can swap them. That's what the algebra laws tell us. So you can also say that this is equal to the probability of B given A multiplied by the probability of A. This useful thing that can come up sometimes in rearranging these equations. You can swap those around, so long as you, again, make sure you apply also the second one, simply because it's the same thing as if you would swap these two around. It all works. And I guess one final note, this is called the multiplication rule. Now, moving on to independence. I mentioned this before. Independence. Well, two events are independent if they have no influence on each other. Written mathematically, it is we know that probability of B and A is equal to the probability of A multiplied to the probability of B, only for two events A and B which are independent. Now, if we have that both the probabilities for the probability of both events A and B are non-zero, we can say that as an additional set of equations, because that first one is sometimes difficult to check, you don't always have all those probabilities when you work with these situations, it can be much easier to check that the probability of B, or A, is equal to the probability of B given A. If they're independent, this will be true, and it also works if you swap them around. So you have A equals, I didn't put Peter, the probability of A given B. These will hold true if they're independent of each other. They will not hold true if they're not independent of each other. But again, this requires that both are non-zero. And then finally, in terms of independence, we have two types of independent relationships. for some number of sets. So if you have some number of A1 all the way up to, AN events, then you have two types of independence: pairwise and mutual. Pairwise isn't very useful, so I'm not going to really go into it. So quick summary: it is event if all they are pairwise independent if all pairs or distinct pairs are independent of each other. It doesn't really come up very much. It's not very useful. The more important one is mutual independence. This states that for all distinct combinations of your events, so maybe it's just the first one, the second one, or the first one, the second one, the fourth one, or all of them, or some other combination, for all possible distinct combinations, if all of them satisfy the equation above, that the multiplication of their individual probabilities is equal to the single probability of their unioned probabilities, then you have, intersection of probabilities, then you have a mutual independence. So the equation then is this one, where you have the probability of AK1, so K1 through Km. This is the part that gives us the all distinct combinations. So K1 Km could be 1 to 3, it should be 1 to n, or it could be 3 to 5, or 3, 5, 7, and 2. It doesn't matter, it is all possible distinct combinations, and we have this equation that multiplying together on the left is the same as what you get on the right. If you have that, then you have mutual independence. And weirdly, this is fairly common, or maybe being able to make the assumption that this is true is fairly common and works. This comes up when you're doing learning and things, but being able to assume that two things which might not be dependent is anyway often works regardless of their true dependence or independence. Though often you have to do some additional things, which we'll get into at a separate video. But yes, if you have this, you have mutual independence. Fairly quick definition. Now let's move on. Where's it up? There it is. Do I not have? Oh, I'm pumped stupid. Didn't put it in a separate section because it doesn't deserve one. It's only quite small. Final bit of this section is about Bayes' theorem, which is a equation. Bayes' theorem is an equation how you can rearrange for finding the probability of some event B given some other event A. If you want to find this and you're presuming that the probability of A is greater than 0, you can use this, so you can find this by finding the probability of A given B multiplied by the probability of B. You might recognize this, we explored it just a moment ago. The reason it's here is for reasons of derivation. If you look up the derivation of line, you can see that that's where it comes from, those equations above. You divide it by the probability of A. If you have this equation, you can use this to find the other thing, the thing on the left. So if you want to swap your two, and you have a limited number of probabilities available, this is one way to do it if you have to have all these. If you don't have this one, the probability of A, you can actually do this using the probabilities of above if you have a couple extra. There is an alternative version of Bayes' theorem, which states that this is also equal to everything the same on the top, but on the bottom, we have that the probability of A given B multiplied by the probability of B, which is the same on the top, I know, plus the probability of A given not B, multiplied by the probability of not B. Now, why is this? Why does it work? It works because, as a useful trick when it comes to probabilities, those two denominators are both equal to each other. That bottom thing represents all the possible situations which could lead to the probability of A. This comes up more when you introduce random variables, because they could have more than one outcome of either it happens or it doesn't, because they can have multiple possible things that can happen. They sort of represent complicated events. Again, separate video. But here it still works with regular, just plain old events. when you have B happening, it can either happen or not happen. So we have two cases. And if you can combine all those cases, sum all of them, which is to say, find this and this, sum them together, didn't put a close bracket there, sum them all together, and that gives you the probability of A occurring. Because A is defined as each of those put together. So by doing so and then dividing by it, you will then normalize with respect to A, which gets you your B given A. Handy bit of trickery that if you want the probability of something, A in this case, and you only know probability of some other thing in all its possible outcomes, B, again, B happening or not happening being the possible outcomes, as well as its relation to the thing you're finding, which is A given B and A given not B, those are the relations to what we're trying to find A, then you can directly find your A just by summing them all together. Because a lot of time, you won't know A. A is some complicated, really difficult to find thing, will take forever and ever and ever to compute, or you just flat out can't find it because you don't have all the information you need. This is the only way to find it. Useful. This is very useful. So that is Bayes' theorem. Comes up a lot when you have the more complicated forms of learning, but also just generally in probability theory, which I'll be exploring in the next video. For now, thank you for watching.